All right, so this video that we're recording here is going to talk about marginal analysis. This term, marginal analysis, is a general term to talk about marginal cost and marginal revenue together as one thing. Whenever we see the term marginal appear, it has to do with a discussion of cost and revenue functions, but it also signals that there's the presence of derivatives in the background, that there's something going on with derivatives here. And marginal analysis is a huge piece of how calculus is involved in economics. And that is, one of our areas of the business math that this class is geared towards. So I'm going to talk first a little bit about marginal cost. So if we're given a cost function, right, we're given some C or C of X, we can call it C equals C of X, where this is the cost of producing X units or X number of product. Then the derivative of this function, remember we used that apostrophe, C prime of X, the derivative of that function is called the marginal cost. So when you're asked to find the marginal cost and you know the cost function, you're being asked to find what the derivative of that function is. So to interpret the meaning of a cost function, or a marginal cost, I should say, is to take the derivative of our function. And we have been using the difference quotient and the limit of the difference quotient to talk about our derivatives, right? Where we have C cost of X plus H units minus the cost of just X units over H. And we'd use that difference quotient, and we're taking the limit as H approaches 0 of that quotient. Since this would be just the definition of the derivative, the formula we've been using, it follows that as we let our H get really small, so as H gets really close to 0, that our derivative becomes approximately the same as the difference quotient. So the marginal cost gets close to our difference quotient, not with the limit anymore, because we're letting that H get very close to 0. And in words, you could say that the derivative or the marginal cost is approximately the cost of increasing, and I think I'm going to have to move over a little bit here, the cost of increasing the number of units we produce, increasing production from X amount to more than that, X plus H amount. That's what this numerator is referring to. And that's just over H. So if we're going to go from having 20 units produced to 30 units produced, then H is 10, and we can calculate the cost, take the difference, divide by 10 to figure out what our increase in production is costing us. But then as we let H get really small, closer and closer to 0, we can sort of discuss this in a different way. In the text, they kind of explain this idea, but their formal piece is to say that the cost, marginal cost, is approximately the cost of producing one more unit, X plus 1, because generally speaking, you can't produce a fraction of a calculator or a fraction of a piece of chalk or whatever you're making. So the smallest we could get without actually being 0 would be 1 more unit. So the cost of producing 1 unit more minus the cost of just producing the baseline number of units. So that's cost of increasing production by 1. So just increasing 1 more calculator, 1 more television, whatever it is that you're producing. So that's our general concept. And we'll see a very similar way of describing what the marginal revenue is like. But let's just work with cost for now. So I'm going to work with a particular example they have in the workbook or in the textbook here, where we're given a cost function, not the marginal cost, but a regular cost function, where c of x equals 1/10 x squared plus 5x plus 1,000. And we're told, this is example 7 from section 13.1, we're told that the cost is being measured in dollars for a weekly production of X tons of steel. And this is the function given to us. So C is cost measured in dollars. X is tons of steel per week measured in tons. So, this might relate to something like Yard Metals, maybe, Penn Steel. Like, those are some of the local companies that produce steel from around here. You may know people that work there. So the marginal cost can be calculated. We can find the marginal cost, and then once we have a marginal cost and this cost function given to us, we can see if we're producing, let's say, 1,000 tons of steel, how much more is it going to cost us to change that to being 1,001 tons of steel? How much more are we spending? And then using revenue, we can also find how much more profit we're making, and is it profitable to increase by 1 unit at a time? So let's focus on finding the marginal cost. So this is the part where we have to use our derivative, our difference quotient definition for our derivative. So to find the marginal cost is to find the first derivative of the cost function, so C prime. And we use the limit as we let h go to 0 of, and we use that difference quotient. So C of x plus h minus C of x all over h. I might need my function in frame for a minute here. So now we can plug in x plus h everywhere that x was located to fill in this value, and then our function as it stands. So let's get started there. The limit as h goes to 0, and this is going to be a big ugly fraction, right? So we have c of x plus h. I'm going to put it in brackets just to kind of section it off. So 1/10 times x plus h squared plus 5 times x plus h plus 1,000. So that's my c of x plus h. I'm subtracting the function the way that it appears, the regular cost function, 1/10 x squared plus 5x plus 1,000. And in my denominator is just an h. Very common mistake is to forget that there is a denominator. It's a good idea to always keep copying that each line of work until you eliminate it at some point. Okay. So next we need to do any distributing and things. We got to work on simplifying the numerator here. This numerator is long and ugly. So I'm going to take the limit as h goes to 0. I know I'm going to have this denominator of h. I can square x plus h squared, so that's 1/10 times x squared plus 2xh plus h squared plus 5 times x plus h. I can distribute that. So I took care of squaring by multiplying x plus h times x plus h. Then I'm going to take 5 and distribute it here. So that's plus 5x plus 5h plus 1,000 minus, and now I'm distributing that minus. So minus 1/10 x squared minus 5x minus 1,000. I do recommend kind of writing out each step as you go because it helps to eliminate making errors when you're combining like terms and things. Before I can combine like terms, I need to distribute that last thing, that 1/10 needs to get multiplied times the 3 pieces in this set of parentheses. Any questions so far? So I'm going to go scroll down to get a little more blank space. Okay. So remember, this is all so that we can take a limit eventually. Right now, I can't take this limit because I'd have 0 in the denominator. So it's all over h. 1/10 x squared plus 2 times 1/10, which is 1/5 xh plus 1/10 h squared, and then I'm copying everything else. All I did was distribute in that last thing in this step. Minus 1/10 x squared minus 5x minus 1,000. Okay. So the only piece that changed was these first 3 terms because I distributed. I multiplied the 1/10 times those 3 terms. Then we look to combine like terms in the numerator. Certainly, I have plus 1,000 minus 1,000. Those are going to cancel out. I also have a subtract 1/10 x squared and a positive 1/10 x squared. So those are going to cancel out. I have a plus 5x and a minus 5x, which is going to cancel out. So I'll write what's remaining here, the limit as h goes to 0 of, and I can write these terms in whatever order I want. It's not very important for like the h squared term to be first or anything. So I'm just going to leave them in this order. So I have 1/5 xh plus 1/10 h squared plus 5h. Everything else in the numerator has canceled out because I had the same thing being added and subtracted. Denominator is still just h. So this is working with that difference quotient. These numbers are a little big and we got some weird fractions, but it's the same steps we've been doing. Next, take out the greatest common factor. For number parts, we've got a 1/5, a 1/10, and a 5. Not really anything too great. Those are all probably going to stay there. I have an x in this term, but none of the other terms have x's. So it looks like the only factor in common is h. We have an h here. We have h times h, because it's h squared in the middle term, and an h in the last term. So I can rewrite this fraction as h times 1/5 x plus 1/10 h plus 5. Right, that 1/10 h, there were 2 h's because it's h squared, so there's still an h there. So just rewriting my numerator to understand where my cancellation is going to come from. H over h can cancel out. Those become multiplication times 1. And that is the step where we're going to be able to actually evaluate this limit after, because there's no longer h in the denominator, which means I'm no longer going to have an issue where I end up with a 0 in the denominator. So I'm left with the limit of a polynomial in 2 variables though, but that's okay. So I can let h go to 0 and evaluate this limit. So that limit is 1/5 times X, that's still there, plus 1/10 times 0 for H plus 5, which means I am about done. I know that 0 times 1/10 is just 0. So C prime, or the marginal cost function, is 1/5 X plus 5. So that is my marginal cost. The cost of producing one more ton of steel. Then my regular cost function that was given to me, I'm just going to copy from the original problem because it's way up high on my whiteboard here. It was 1/10 x squared plus 5x plus 1,000. So this is the original cost function given in the problem. Here is my marginal cost that I have now figured out by taking that derivative. I think it's interesting to look at how the two compare a little bit and interpret a bit. So let's say we want to find out what the cost and the marginal cost will be when we produce 1,000 tons of steel. So for 1,000 tons of steel, I'm not gonna spend a ton of time showing out the calculation for this. It's just plugging in the number 1,000 into each of these functions. So we can evaluate the marginal cost, C prime of 1,000, by plugging in 1,000. 1/5 times 1,000 is 200 plus 5 means that my marginal cost is $205 per ton. Where the regular cost function, I'm plugging in that 1,000 for X, 1/10 times 1,000 squared plus 5 times 1,000 plus 1,000. And you can calculate that out where we get a total of $106,000. So that's the cost for 1,000 tons. So the interpretation here is that with the regular cost, if I make 1,000 tons of steel, it's going to cost me a little over $100,000, $106,000. Where the marginal cost, that 205, means that the cost of producing one additional ton after the 1,000 tons is already done is an extra $205. The average cost can also be calculated, but that's going a little bit further than I would like to in this example. Again, so when we talk about revenue, revenue is the amount of money you're getting from selling the item, right? It's not the same as profit. Profit is like you take your revenue and subtract the cost to talk about profit. But our revenue here with the steel producer would be like R, or R of X, where R is the total revenue received from selling X tons of steel. So total money or revenue received from selling X tons of steel, if I'm still in that specific example. The derivative of R is going to be called the marginal revenue. So the marginal revenue, just like marginal cost, is going to be measured in dollars per ton. It's how much money additional am I making for another ton of steel being sold now instead of produced. And we use basically the same type of thing. We have r prime, or first derivative of r, is equal to, and you can use that limit to get an exact, the limit as h goes to 0 of r of x plus h minus r of x over h. And we can also talk about the marginal revenue as being approximated as we let h get really small. It's approximately that difference quotient, r of x plus h minus r of x over h. So as h gets really tiny, that limit portion kind of disappears. And in fact, our summary from the author is that the marginal revenue, r prime of x, is r of x plus 1, just producing 1 extra ton, minus r of x. And that tells us the revenue that results from selling 1 more ton of steel than whatever x was. So again, working with that same steel formula, if we have a revenue function given to us, not the marginal revenue, but the regular revenue function, r of x for our steel is given as x squared plus 5x. Revenue measured in dollars for tons of steel, which is what x is. And this function is given. We can find the marginal revenue and then evaluate the marginal revenue for when we sell that 1,000 tons of steel. And see for every additional ton of steel we make, what the revenue increases by, or if it could potentially decrease as well. Looking at this expression, I'm thinking that it's going to increase. So finding the marginal revenue is to take the first derivative of x squared plus 5x, which I'm writing incorrectly, but we're going to take the limit as h goes to 0 of r of x plus h minus r of x over h. So that's the limit as h goes to 0, which I'm not going to be able to plug 0 in right away because of that 0 in the denominator issue. But we have x plus h squared plus 5 times x plus h. And again, just for clarity, I'm going to put some brackets around that. Subtract x squared plus 5x. And all of that's over h. So just plugging in my function for revenue and my function for revenue, but evaluated at x plus h instead of just x. Then it is, algebraically simplifying this fraction to cancel the denominator eventually. So we can square where we need to, distribute where we need to. So x plus h squared is x squared plus 2xh plus h squared. Plus 5 times x plus h is 5x plus 5h. Subtract, and we're distributing that. So I took care of the square. I took care of distributing 5. And now I'm distributing that negative sign. So minus x squared minus 5x. These numbers were a little friendlier. We didn't have those fractions and such. So all of our distributing is done. There's no more parentheses to worry about. Time to cancel where we can. I have a positive x squared minus x squared, a positive 5x minus 5x, and then everything else that's left, none of those terms can be combined. They're not like terms. So we've got 2xh plus h squared plus 5h. So same type of steps, distribute where you can, get things combined so it simplifies down a little bit. Then take out whatever's the common factor. As you get a little more practice, you might not write this step out, but it's definitely a good idea to help ensure less mistakes are made. So I factored out h, right? So h came out of the 2xh, leaving just 2x. Instead of h squared, one of the h's came factored out, so it's just h. And instead of 5h, I took the h out, so it's just a 5. Then we can cancel between numerator and denominator. And we no longer have an issue with 0 in the denominator because our denominator is gone. I can evaluate this limit by plugging 0 in for h, and I get left with 2x plus 0 plus 5. So just 2x plus 5. So that was just taking a derivative. Now relating it back to the revenue. This marginal revenue is 2x plus 5. The original revenue function that was given in the problem was x squared plus 5x. So if I sell that 1,000 tons of steel that I was talking about in my cost problem, the revenue was to take 1,000 and plug it into the revenue function. So 1,000 squared plus 5 times 1,000. And use your order of operations here. Square first, then multiply, then add, and you should get slightly more than $1 million. Revenue for selling those 1,000 tons of steel is 1,005,000. Oops, too many zeros. So thinking back to the cost from the previous part when we were doing the cost, our regular cost for selling 1,000 tons of steel was $106,000. And now when I sell that, after I've paid the $106,000 to make it, I sell it for way more than $1 million. I can also observe the difference between the marginal cost and marginal revenue. So my marginal revenue, R prime of 1,000, is going to be 2 times 1,000 plus 5, which tells me my marginal revenue for selling 1,000 tons of steel is $2,005 per ton. So that $2,005 per ton means that the revenue I'm gaining from selling just one more ton after that 1,000, for selling 1,001 tons of steel, is going to increase my revenue $2,005. It doesn't necessarily speak volumes for selling more than 1,001 though. So it's very specific to that exact point, just producing production by 1 ton. And the cost was $205 per ton, I think, if I remember right. Yeah. The marginal cost had been $205 per ton. So I think I got to stop sharing because I can't select the thing to stop